June 23, 1944, Central Atlantic, roughly 870 nautical miles west of Cape Verde. In the tight control compartment of the Japanese transport submarine I-52, Commander Uno Kameo monitored the final moments of a covert meeting at sea. His vessel carried a strategic cargo, about 2 tons of gold, more than 100 tons of tin, and additional materials intended for German-controlled France. Through the periscope, he observed the German submarine U-530 fading into the night after delivering radar gear and 2 specialists. The exchange had gone as planned. The next step was a nighttime surface run toward Europe at about 15 knots beneath a clouded, starless sky. Nothing appeared out of order. Less than 3 hours later, Kameo and the 94 sailors aboard I-52 would be killed. They fell victim to detection systems they did not know were present. As their submarine was torn apart, the acoustic signatures of the sinking were captured by American forces. Aircraft overhead monitored the ocean through floating listening devices, recording the destruction on wire recorders. These floating sensors, dropped by a U.S. Navy Avenger torpedo bomber, transmitted underwater sounds to operators in the air, allowing them to pinpoint the submarine's final moments. The loss of I-52 was more than a single operational success. It symbolized a deeper shift, the erosion of Japanese confidence in their undersea fleet. Waters that once served as Japan's strategic corridors had become a monitored zone dominated by American detection networks. The imbalance in technology and production was already being reflected across the Pacific in hard numbers that challenged Japanese assumptions about their reach and survivability. From 1941 through 1945, U.S. submarines sank 1,314 Japanese vessels, totaling roughly 5.3 million tons, over half of Japan's merchant shipping losses. Japanese submarines, despite advanced engineering and large displacement, destroyed only 184 Allied ships, amounting to about 1 million tons. The gap was not merely statistical. It reflected fundamentally different approaches to submarine warfare, industrial capacity, and technological development. Japan invested in exceptionally large submarines, including designs capable of carrying aircraft or traveling immense distances. The United States focused on detection and mass production. Sonar improvements, radar, sonobuoys, and acoustic torpedoes were manufactured in quantities Japan could not match or counter effectively. The shift in dominance emerged gradually. Repeated encounters at sea made Japanese crews aware they were being located and attacked by unseen systems operating on a vast industrial scale. Lieutenant Commander Nobuki Onambu, who later commanded the large submarine aircraft carrier I-401, would explain after surrendering in August 1945 that his realization of defeat came not. Routine transmissions revealed abundant resources, efficient coordination, and large-scale operations spanning thousands of miles, capabilities Japan could not replicate. For many submarine crews, however, the realization arrived through direct confrontations with American anti-submarine technology that left survivors shaken and discouraged. The process by which Japanese submariners recognized American technological dominance unfolded over time. It was not defined by a single decisive battle or dramatic last stand, but by repeated experiences that revealed an overwhelming disparity in production, detection, and coordination. Gradually, confidence gave way to the understanding that their mission had become untenable long before Japan formally capitulated. When Japan entered the Second World War in December 1941, its submarine arm ranked among the most advanced on the planet. The Imperial Navy fielded roughly 70 long-range submarines, many incorporating bold engineering concepts. Among them, the I-400 series stood out. Before the arrival of nuclear submarines in the 1962, these were the largest ever built, stretching about 400 feet and displacing nearly 5,900 tons while submerged. The I-400 boats were designed as mobile strike platforms. Each carried up to 3 Mi-6 Sea-Ran floatplane bombers inside a sealed hangar. The aircraft could be assembled on deck and launched by catapult, giving the submarines the theoretical ability to hit distant targets such as the Panama Canal or even New York. Their range was extraordinary. Fuel stores allowed voyages equal to 1.5 trips around the globe without refueling. At cruising speed, they could cover roughly 37,500 nautical miles, a remarkable achievement for the era. Technical features included specialized ballast and trim systems for extended submerged waiting, degaussing cables to reduce vulnerability to magnetic mines, air search radar, and early sound dampening coatings intended to weaken enemy sonar returns. Other Japanese submarines were also capable. Type C transport boats like I-52 could sail more than 21,000 nautical miles while carrying strategic cargo between Japan and its partners. Fast attack submarines operated across the Pacific using long-range torpedoes and respectable underwater endurance. Crews underwent intensive training in stealth, navigation, and coordinated operations. Many officers and sailors had years of experience before the war's midpoint. Commander Tatsunosuke Arizumi, later responsible for submarine operations, was regarded as one of Japan's most skilled undersea tacticians. Confidence among crews was high, and early wartime results seemed to justify it. In the opening months, Japanese submarines supported the attack on Pearl Harbor, conducted reconnaissance, screened fleets, and pursued Allied warships. Their operational doctrine prioritized fleet support, scouting, and strikes against high-value naval targets, unlike U.S. submarines, which increasingly focused on destroying merchant shipping. Japan largely reserved its boats for tactical missions against warships. This choice would have serious consequences. While Japanese submarines hunted carriers and cruisers, American submarines systematically targeted the merchant vessels that sustained Japan's industry and logistics. At the same time, Japanese crews increasingly encountered Allied anti-submarine defenses in heavily protected combat zones where detection systems were strongest. By 1944, Allied technology had advanced dramatically, including the introduction of sonobuoys. These devices were small, battery-powered sonar transmitters dropped from aircraft. Once in the water, they floated and listened for underwater noise, sending signals by radio back to the patrol plane. Originally developed by Britain in 1944 under a secret program, they were rapidly refined and widely deployed by the United States. Their effect on anti-submarine warfare was profound. Previously, aircraft had to keep a submarine in sight or rely on radar, which worked only when the target was surfaced. A submerged submarine was otherwise very difficult to track. Sonobuoys changed that. Aircraft could scatter several buoys in a pattern, creating a listening grid. By monitoring each buoy in sequence, crews could detect propeller sounds or mechanical noise and follow a submarine's movement beneath the surface. By late 1944 and into 1945, such equipment became standard on Allied patrol aircraft. For the crew of the transport submarine I-52, the danger became clear late on the night of June 23, 1944. An Avenger torpedo bomber from the escort carrier USS Bogue, piloted by Lieutenant Commander Jesse D. Taylor, picked up the submarine on radar while it traveled on the surface. Flares were dropped, exposing the vessel, and depth charges followed as the submarine attempted an emergency dive. The first attack bracketed the target but failed to destroy it. Taylor then deployed a sonobuoy. Almost immediately, the aircraft's radio operator heard the distinct rhythm of the submarine's propellers transmitted from the floating sensor. Using that information, Taylor tracked I-52's evasive maneuvers underwater, anticipating its path and positioning for another strike. He released a Mark 24 acoustic homing weapon nicknamed Fido, which locked onto the noise of the submarine's propellers and pursued it until impact. The sonobuoy continued to transmit, capturing the detonation and the sound of the hull breaking apart below the surface. Commander Taylor's team reported hearing sharp grinding sounds, metallic snaps, and crushing impacts reminiscent of a can collapsing under pressure. Soon after, the submarine I-52 plunged to the seabed nearly 17,000 feet below the surface. With it went Commander Cameo, 94 crew members, 14 passengers, and 2 German technicians. None survived. Recordings captured by sonobuoy equipment were later preserved in the U.S. National Archives on thin wire reels labeled Gordon Wire No. 1 and Gordon Wire No. U.2. These fragile recordings document the final minutes of a submarine crew that never understood the technology responsible for their destruction. The loss of I-52 revealed capabilities that deeply unsettled Japanese submarine forces once fragments of information spread through intelligence channels. American aircraft had developed the ability to detect submarines even while they were submerged. The consequences were profound. A Japanese submarine diving to evade an aircraft was not truly escaping. It was only disappearing from sight while remaining detectable through sound. U.S. hunter-killer groups built around escort carriers such as USS Bogue combined radar, sonar buoys, and acoustic torpedoes into coordinated systems. Submarine warfare shifted from random encounters to methodical tracking and elimination. The task group centered on USS Bogue alone accounted for the destruction of 13 German and Japanese submarines between early 1943 and mid-1945. Using these techniques, Japanese crews began reporting puzzling incidents. Aircraft appeared above their dive locations with uncanny precision. Depth charges fell in carefully arranged patterns despite the submarine being far below the surface. Torpedoes seemed to pursue evasive maneuvers as though guided by unseen control. They were facing technologies their navy had neither fielded nor fully understood. The psychological strain intensified in June 1945 during Operation Barney. 9 U.S. submarines equipped with FM sonar entered the Sea of Japan through heavily mined passages long believed impenetrable. Japanese planners considered these waters secure, shielded by dense mine barriers, especially in the Tsushima Straits where merchant vessels operated under the assumption that enemy submarines could not pass. FM sonar, designed to identify underwater hazards, produced a distinctive ringing tone whenever it detected mines. American sailors nicknamed the sound Hell's Bells. Using this system, submarines could chart mine patterns, locate gaps, and thread safe routes through barriers that Japanese engineers thought impossible to breach. On June 4, 1945, the first trio Sea Dog, Crevalle, and Spadefish slipped into Tsushima Strait while submerged. Their sonar displays mapped the minefield in real time. The warning chime sounded constantly as they maneuvered between mines, sometimes spaced only about 50 yards apart. After roughly 20 hours underwater, all three reached the Sea of Japan unharmed. Additional groups followed, and within days 9 American submarines were operating freely in waters Japan had considered untouchable. Their results were dramatic. From June 9 to June 24, 1945, the 9 submarines sank 28 Japanese vessels totaling nearly 55,000 tons, including both a destroyer and a submarine. They surfaced at night to recharge batteries and submerged by day to strike targets that assumed themselves beyond reach. Japanese naval leadership was stunned as reports arrived describing attacks deep inside supposedly protected waters. Survivors spoke of American submarines moving with little resistance, attacking and withdrawing at will. The psychological impact was severe. If even the most heavily defended seas could be penetrated, nowhere felt secure. Japanese submarine commanders quickly grasped the broader implications. They were confronting an adversary with technological tools Japan could not match. Patrols increasingly became exercises in survival rather than effective combat operations. The gap extended beyond sonar. American submarines carried radar capable of detecting surface contacts more than 20 miles away under favorable conditions. Japanese submarines did not begin receiving radar until mid-1944, and even then in small numbers with inferior performance. This allowed American boats to locate targets first, track them beyond visual range, and position for attacks with decisive informational advantage. American forces also benefited from code-breaking efforts that deciphered Japanese naval communications. Submarine schedules, patrol routes, and operational plans were often known in advance. Combined with superior detection systems, this meant Japanese submarines operated in waters where the enemy frequently knew their positions and intentions. Lieutenant Commander Nukio Nambu of I-401 later described to American interrogators a constant sense of surveillance, never feeling secure, even while submerged in open ocean. The anxiety, he admitted, reflected reality rather than paranoia. Industrial capacity further widened the gap. Japan struggled to keep about 70 submarines operational during the war, while the United States built 314 between 1941 and 1945. Losses were replaced faster than combat could inflict them. American shipyards worked continuously, launching fleet submarines at a pace Japanese planners considered unattainable. Facilities such as Mare Island Naval Shipyard in California, Electric Boat in Connecticut, and Portsmouth Naval Shipyard in New Hampshire operated in synchronized production cycles. The submarines themselves embodied this industrial strength. U.S. Gato and Belisle-class boats, though smaller than some Japanese designs, were built using standardized components manufactured across dozens of factories. Engines, batteries, torpedoes, optical equipment, and sonar units were produced separately and delivered in coordinated supply chains. A single Gato-class submarine required roughly 140,000 individual parts from contractors spread across 32 states. The flow of materials rarely faltered, and when repairs were needed, replacement components were readily available. When American submarines were lost in action during the Pacific War, replacements were delivered quickly thanks to the United States' massive shipbuilding capacity. Japanese submarines, by contrast, often remained in dock for extended periods after sustaining damage. Shortages of spare parts, overwhelmed repair yards, and limited industrial throughput meant that even minor repairs could take weeks or months. Delays the U.S. Navy rarely faced. The disparity between the two nations was especially clear in torpedo development and production. At the start of the war, American submarines were equipped with the Mark 14 torpedo, a weapon that proved deeply flawed. It frequently ran at the wrong depth, its magnetic exploder malfunctioned, and its contact detonator often failed on impact. For almost 2 years, U.S. submarine crews attacked enemy shipping with munitions that sometimes passed harmlessly beneath targets or struck without exploding. This period could have offered Japan a strategic opening. Instead, American crews themselves investigated the malfunctions. Submarine officers carried out field tests, documented failures, and pushed for corrections even as the Bureau of Ordnance resisted their conclusions. By late 1943, most of the Mark 14's critical defects had been resolved. Around the same time, a new electric torpedo, the Mark 18, entered service. Because it left no visible wake, it denied enemy ships any warning of an incoming strike. Aircraft also began deploying the Mark 24 Fido, an acoustic homing torpedo that tracked the sound of submarine propellers after entering the water. Japan never fielded comparable systems. Its torpedoes were generally dependable, but they lacked the technological innovations appearing in U.S. arsenals. Even more limiting was production capacity. Japanese industry could not manufacture weapons in the quantities needed for sustained operations. American submarines typically sailed with around 24 torpedoes and could expend them freely, confident that more would be available at the next base. Japanese submarines carried fewer and had to conserve them carefully because replacements were uncertain. Over time, the cumulative impact of these differences became unavoidable. Each patrol reinforced the same conclusion for Japanese crews: American control of the sea lanes was tightening. By 1944, the peak year of U.S. submarine operations, American boats were sinking roughly one Japanese vessel per day. That year alone saw 492 merchant ships, totaling over 2.3 million tons, destroyed by submarine attack. Japan could not build replacements fast enough. Its merchant fleet, about 6 million tons in 1941, had fallen to roughly 2 million by mid-1945, with only a fraction still able to transport cargo. The collapse of shipping had consequences far beyond naval losses. It choked Japan's entire war economy. Food from Southeast Asia struggled to reach the home islands. Oil shipments from the Dutch East Indies dwindled. Essential resources, rubber, tin, tungsten, remained stranded in overseas territories while American submarines dominated the routes between them. By the final year of the war, U.S. submariners sometimes found it difficult to locate worthwhile targets simply because so few Japanese cargo ships remained. Survivors hugged coastlines, moved through narrow channels, or stayed in port rather than risk destruction. After the war, Japanese officials openly acknowledged that the destruction of their merchant fleet had been a decisive factor in defeat. Some concluded that American submarines had contributed more to the outcome than any other single weapon system. For Japanese submarine officers who later observed American technology up close, the realization was stark. Captain Tatsunosuke Arizumi, closely associated with the massive I-400 submarine program, took his own life aboard I-401 rather than surrender. He and others had come to recognize that Japan had challenged an industrial opponent whose technical and manufacturing capabilities far exceeded their expectations. The surrender of the giant I-400 class submarines in August 1945 illustrated the contrast. When USS sailors boarded these enormous underwater aircraft carriers, they were impressed by their scale and advanced design. Longer than many destroyers and larger than any American submarine, they appeared almost futuristic, yet they had achieved nothing in combat. Planned operations such as strikes against Ulithi Atoll or even the Panama Canal were never carried out. In the end, these remarkable machines consumed vast resources but contributed little, their missions rendered impractical by overwhelming American industrial and technological superiority. American anti-submarine defenses made it nearly impossible for Japanese submarines to approach their objectives without being detected. Operating covertly in waters controlled by the United States was extremely dangerous. Patrol aircraft, radar coverage, sonar networks, hunter-killer task groups, and acoustic torpedoes formed a layered system that the US's Navy had refined into a highly effective method of submarine hunting. Japanese boats entering these zones faced overwhelming risks. When American forces inspected captured Japanese submarines, they found vessels that combined sophisticated engineering with serious design flaws. Their pressure hulls could not safely dive as deep as comparable American or German submarines. Sonar detection was another weakness. The size and structural characteristics of these submarines produced sound signatures that U.S. sonar crews could track from long distances. Radar equipment was absent from most Japanese boats until late in the war, and they lacked an equivalent to American frequency-modulated sonar for detecting mines. Their anti-aircraft armament also proved insufficient against increasingly effective U.S. aerial patrols. Perhaps the most consequential shortcoming was the absence of advanced integrated fire control systems. American submarines relied on onboard computing devices that calculated torpedo solutions automatically, factoring in speed, course, range, and weapon performance. Japanese crews depended on manual plotting, which took more time, increased the chance of error, and exposed them longer during attack runs. These differences were not minor, they affected nearly every operational aspect of submarine warfare. The result was severe losses. Over the course of the conflict, Japan lost about 130 submarines, a proportion significantly higher than that of the United States. From the roughly 70 submarines Japan had at the start of the war, plus those constructed afterward, most were destroyed by U.S. anti-submarine tactics, sonar tracking, radar detection, air attacks, depth charges, and coordinated hunter-killer patrols. Casualties among submarine crews were devastating. Around 10,000 Japanese submariners died, producing a loss rate of more than 70%. What had once been seen as a prestigious and elite service gradually came to be viewed as extremely dangerous, even fatal. Recruits and their families understood that assignments to submarines carried grim statistical odds of survival. By the war's end, Japan's submarine force, once a symbol of naval pride, had been reduced to a demoralized remnant, its operational effectiveness undermined by technological disadvantages. The psychological impact on Japanese submariners developed differently from that experienced by German prisoners of war in the United States, but both groups arrived at similar conclusions. German captives witnessed American industrial abundance firsthand, while Japanese submariners encountered American technological superiority in combat. Each group recognized that their nations had confronted an opponent with far greater industrial and technical capacity. After Japan's surrender in August 1945, surviving submarine officers and crew were confronted directly with the scale of that superiority. Many were taken aboard U.S. submarines where they observed unfamiliar equipment and systems. They visited American naval bases and saw production facilities that explained the steady flow of supplies and vessels that had supported U.S. operations. They examined sonar devices, radar installations, mine detection systems, and acoustic torpedoes, the very technologies that had contributed to their losses. One example involved Lieutenant Commander Nambu, who surrendered with submarine I-401 and was brought aboard the American submarine USS Segundo. During a guided inspection, he studied its radar arrays, sonar gear, fire control computers, and torpedo handling systems. Each component appeared more advanced and, importantly, more reliable than the equipment he had known. U.S. submariners operated with a confidence grounded in dependable machinery and consistent logistical support. Their crews expected to survive patrols and return safely. Japanese crews, by contrast, had long operated under the assumption that American technology gave the enemy a persistent advantage in detection and attack. Nambu later told interrogators that he realized Japan's defeat months before the atomic bombings. While monitoring U.S. radio communications, he heard the routine coordination of large-scale operations across vast ocean distances. The efficiency, resource availability, and technical precision evident in those transmissions suggested capabilities far beyond what Japan could match. After the war, additional evidence reinforced these impressions. Japanese submariners were taken to American-controlled bases in Japan locations such as Sasebo, where captured vessels were examined and catalogued. They also witnessed surrender ceremonies in Tokyo Bay, where American submarines were prominently displayed. During the formal signing aboard USS Missouri on September 2, 1945, Vice Admiral Charles A. Lockwood, commander of USS submarine forces in the Pacific, made a symbolic gesture by raising his flag aboard captured Japanese submarines. The message was unmistakable. The outcome of the undersea war had been determined largely by industrial strength and technological superiority. When the submarines I-400 and I-41 were brought to Hawaii after the war, U.S. naval specialists began a careful technical review of the vessels. Japanese sailors who had operated them were present as advisors, observing as American teams dismantled the boats piece by piece. Every system was photographed, measured, and catalogued. The Americans showed respect for certain engineering solutions, yet they felt no sense of threat. By then, they understood that the defeat of Japan's submarine force had come less from seamanship than from a decisive edge in technology and the immense production power behind it. The final chapter unfolded in 1946. Several captured submarines, including the large I-400 class boats, were towed out to sea near Hawaii and intentionally sunk during target exercises. One motive for the decision was the Soviet Union's request to inspect the vessels. Rather than allow Soviet engineers access to advanced Japanese designs, U.S. authorities chose to eliminate them. For Japanese submariners, who later heard of the Scuttling, the message was unmistakable. Machines once seen as the pinnacle of their navy's ingenuity were now surplus, destroyed without ceremony by a nation that had already moved beyond them technologically. American submarine development had progressed to a point where little could be gained from further study of the captured boats. What had symbolized Japan's maritime ambition became little more than practice targets, scarcely noted in U.S. records. Among Japanese crews, the lesson spread quickly. Impressive design alone had not been enough. American industrial strength and integrated technological systems had rendered Japan's efforts obsolete. After the war, returning submariners shared their experiences in memoirs, lectures, and veterans associations. Discussions repeatedly focused on why a fleet built with notable engineering skill had achieved so little operational success. The conclusions were consistent. Japan's submarines suffered from technological gaps, limited industrial support, and flawed strategic use. Courage and professionalism could not offset structural disadvantages. Across detection systems, communications, navigation, and logistics, U.S. submarines operated with a clear technical advantage. These reflections influenced Japan's post-war rebuilding. Veterans carried their wartime lessons into civilian industry and defense planning. As the country rebuilt in the 1950s and 1960s, companies and policymakers emphasized precision manufacturing, reliability, and continuous improvement rather than grand but isolated achievements. The experience of projects like the I-400 program, ambitious yet strategically ineffective, reinforced the need for coordinated systems and consistent quality. Major firms such as Sony, Toyota, and Honda adopted these principles, focusing on technological depth, dependable production, and incremental refinement. Former naval officers, including those with submarine experience, entered corporate roles and contributed to this shift in thinking. Over time, Japan's industrial philosophy was shaped in part by the recognition of American technological and organizational superiority during the war. By the 1960s and 1970s, the Japan Maritime Self-Defense Force began integrating U.S. technologies into its own submarine fleet, training with American instructors, adopting similar sonar equipment, and building vessels with U.S. collaboration marked a new era. Former adversaries became security partners, united by the understanding that modern warfare depended on technological sophistication and industrial capacity. For the submariners who had lived through defeat, this transformation confirmed their conclusions. Japan's future lay in matching leading technological standards rather than pursuing isolated feats. By the 1982s, Japanese submarines ranked among the most advanced in the world, reflecting decades of lessons drawn from wartime failure. Archival recordings of the destruction of submarine I-52, preserved in American collections, later offered further evidence of the technological shift that had defined the conflict. Analysis by specialists at Johns Hopkins University's Applied Physics Laboratory demonstrated that acoustic homing torpedoes guided by signals from deployed sonobuoys had played a decisive role in its sinking. These findings underscored how advances in detection and guidance systems had transformed undersea warfare and shaped its outcome. The destruction of Commander Kamo and his crew in June 1944 illustrated a technological gap Japan never managed to close during the war. The tools responsible, advanced sonar, radar detection, and homing torpedoes, were early versions of systems that later became standard equipment in navies across the globe. What Japanese submarine crews encountered in the final years of the conflict was not simply a stronger opponent, but a transformed battlefield shaped by rapid innovation. For many submariners, the realization that the seas were no longer a safe operating space unfolded gradually. American forces had introduced detection and tracking systems that made concealment increasingly difficult. Industrial production allowed these technologies to be deployed widely and refined quickly. In this environment, bravery and seamanship could not compensate for the widening technological imbalance. Japanese crews were neither lacking in skill nor resolve. They were confronting an adversary with overwhelming scientific and manufacturing advantages. A similar psychological shift occurred among German prisoners of war held in the United States, though under different circumstances. Both Japanese submariners and German captives found themselves facing American capabilities that seemed inexplicable at first and undeniable by the war's end. Many who returned home carried with them a clear understanding that post-war recovery would require not only rebuilding but also catching up technologically and industrially with the United States. By late 1944 and into 1945, anti-submarine warfare had become a coordinated system. Aircraft dropped sonar buoys that transmitted underwater sounds to operators above. Radar scanned vast areas of ocean beyond visual range. Homing torpedoes could track submerged targets without direct guidance. Surface ships and aircraft operated in integrated hunter-killer groups, methodically reducing submarine threats. These developments left Japanese submarines with few safe routes and even fewer opportunities for survival. The situation became undeniable by mid-1945. When American submarines carried out Operation Barney and penetrated the heavily defended Sea of Japan, sinking numerous ships in waters considered secure, it demonstrated that technological superiority could overcome even the strongest defensive measures. If minefields and patrol zones could be navigated through advanced equipment, the strategic balance had shifted irreversibly. For Japanese submarine crews, the lesson was harsh but clear. They had been located, pursued, and destroyed by systems they could not effectively detect or counter. Survivors recognized that once American industrial output and research capabilities reached full strength, Japan's defeat was only a matter of time. The war beneath the waves had been decided less by individual heroism than by engineering, science, and production capacity. These experiences influenced post-war thinking in Japan. Returning sailors and officers understood that future security and prosperity would depend on technological development and industrial strength. Their observations contributed to broader national efforts to modernize and compete in a world where innovation determined power. Today's naval forces still rely on descendants of the systems that changed the course of the undersea war. Sonar networks, radar surveillance, and advanced torpedoes remain central to maritime operations. Modern submarines employ technologies far beyond what was imaginable in the 1942, yet the underlying principle has not changed. In modern conflict, the side that combines innovation with large-scale production holds a decisive advantage. The submarines that once symbolized Japanese naval ambition now rest as relics, either preserved in museums or lying on the ocean floor. They stand as reminders of a conflict in which technological transformation reshaped the balance of power. For the crews who experienced that shift firsthand, the war became a lesson in how rapidly scientific and industrial progress can redefine control of the seas.